Howdy folks, it's me, Mr. Hess, back to teach you another section from Chapter 9. We've been focusing on circles in this chapter, and in Section 5, the title of this one is Tangents. Okay, if you look at the word tangent, it makes sense because, see this line? This line is what we would call a tangent. Notice that the line intersects the circle at just a single point right there. So it almost looks like this circle is like some kind of a ball or something resting on the ground, where the line would be the ground. And of course that ball would only come in contact with the ground at that one single point. Okay, so a tangent gets its name from the fact that something that is tangible means you could touch it. And this line, as you can see, just grazes the circle, just touches the circle at that single point. So that's why we call that a tangent. Whereas opposed to, there's another possibility. You know, if a line's going to intersect the circle, most of the time, instead of just touching at one point, it would look something like this, where the line goes through the circle at two different points. Now that has its own name. That's what we call a secant. Okay, my way of remembering the difference between the two, again, tangent means just touches. Okay, and secant, I think of an old military phrase, seek and destroy. You know, so this has, if you think of it like a projectile, it hit its target and went through the target, you know. So it's seek and destroy. Secant will hit the circle at two different spots like that. Okay, but again, this section is going to focus on the tangent, not the secant, although you will see different pictures of secants involved in the problems that we do still in this section. Okay, but the point of this section is to focus on the tangent, and right there where it touches, that's referred to as the point of tangency. And that's important because if we draw now a segment from the center of the circle to that point of tangency, notice that not only is that a radius of the circle, you know, that's an R, a radius, but your gut instinct may be kicking in at this point too. That radius will have a certain relationship to the tangent, and I hope you can kind of guess here and see it. They're always going to be perpendicular. They're going to form a right angle there. Okay, so that idea that the radius drawn to the point of tangency will always meet a tangent at a right angle, or be perpendicular, is covered in Theorem 9.8 of your postulates and theorems. Okay, and Theorem 9.9 is simply the converse of this. So Theorem 9.8, you know, would, if I give you caveman talk, say that if tangent, then R would be perpendicular to the tangent. Okay, Theorem 9.9 is just a converse of this idea. So it's going to switch the two. So it would start out by saying, if they are in fact perpendicular, okay, then we know the line is a tangent line. So if we draw a radius and it's perpendicular to that line, then we know it has to be a tangent line, just touching the circle at a single point. Okay? But, you know, let me tidy this up a little bit. Again, if we have a circle, we have a tangent line coming in here and just touching the circle at a single point. Then if we draw from the center of the circle a radius, it's going to form a right angle. Now, the problems we're going to do in this section are going to do this, though. They're going to also create a secant by doing this. Now, instead of drawing the full secant going all the way through the circle, you know, they don't do this. They don't go all the way through the circle. They're stopping it short. But notice then that segment there is part of a secant that would hit the circle at two different points. Okay, but more importantly, I want you to notice that when we finish this off here like this, it creates a right triangle. Okay, and of course, I bet you know where I'm going to go with this next. Whenever there's a right triangle involved, that means we can also make use of the Pythagorean theorem. A squared plus b squared equals c squared. So any problem that you see that involves a radius meeting a tangent at the point of tangent C, just remember that's a right angle, making a right triangle, Pythagorean theorem. Okay, now there was one more theorem, a theorem 910. I'm going to start with a fresh board here for that one. And in this theorem 910, it says that we're going to start with a point outside of the circle. So something maybe out here. Okay, and then it turns out that from that point outside of the circle, which I'm going to call point A here, you can draw not one but two different tangents. You know, I could have a tangent that would come up over here and just touch the circle right here where I'm going to call point B. So AB is a segment that's tangent. Now, by the way, to be a tangent segment means that if I were to keep going with this, it would be a tangent line as well. Okay, so you can't just do something like this where you just go, oh, look, it touches at one point. That's a tangent. No, that's not. That's a secant. If I kept going with that, see how it would hit the circle at two different points? Okay, so be careful. You can't just do that. But there is another tangent I can make. I did a tangent to point B up above, and now I could do one down here that would just touch the circle down below here as well. Okay, so I've got an AB and an AC, both tangent to the same circle. All right, now according to theorem 910, it turns out that the two tangents I just made, AB and AC, they will be congruent. So AB and AC in this picture, according to theorem 910, should be congruent. I jokingly call it the dunce cap effect. If you know what a dunce cap is, it's kind of like, well, when you go to a birthday party, you wear the little cone hats, you know, that come up to a point. Okay, a dunce cap was a similar type of cone-shaped hat that was real tall, and it said dunce on it. And back in the old days, they would put that on a student that was that maybe did something really dumb, and they were really cruel back then. And as a way of making fun of them, dunce really just meant stupid. So they would make a kid wear that and sit in the corner of the room, and all the other kids would laugh at him and point at him and stuff. So this kind of looks like that. If you look, here's a smiley face, there's the eyes, and there's our dunce cap. See it? It's a little pointy hat on the top of the head of our circle here. Okay, but those are going to match on each side there. So I jokingly call that the dunce cap effect. It's an easy way to remember this. Now I do want to show you why it works, because it turns out there's all kinds of stuff that we could show in this picture that are going to be congruent. So let's say here's the center of the circle. Okay, I'll call that point D. So D to B, do you see as a radius? And that radius is meeting the point of tangency. So our previous theorem said that this will be a right angle right there. Okay, now if I draw D to C, that's another radius. So I know that this and this match. So let's pretend I didn't know this yet. Pretend I didn't know those match. Okay, so I've got a radius and a radius. Again, this radius should meet this tangent at a right angle. Okay, and then I'm going to draw a segment from D to A, splitting this, as you can see, into a couple of right triangles. Okay, and we already know that from D to A has to be the same length for both triangles because they literally share it. So DA is congruent to itself. Remember, that would be the reflexive property in a proof. we would say that those are congruent. Okay, and at this point now, you can actually state that the two right triangles are congruent. We could say that this triangle ABD would have to be congruent to the mirror image of it. See how you just reflect this and flip it down? So ACD. And I know that they're congruent by one of the methods that we've learned previously in our geometry class. Remember, we had different ways to prove triangles congruent. We had SSS, SAS, ASA, AAS, and one fifth way that only worked for right triangles called HL. And what do you know? Across from the right angle, that's the hypotenuse. This is one of the legs. So we could say that these triangles are congruent, these right triangles are congruent by HL. And if the triangles are congruent, then we can finally say that this side and that side, AB and AC, are congruent. And it turns out we could say it's by CPCTC. Because if the triangles are congruent, then all their corresponding parts of the congruent triangles have to be congruent. In particular, those corresponding parts. So again, just think of it as a mirror image. Okay, if you think of it that way, if this is just a reflection of that one, then that means not only do those sides like here and here match, there and there, angles match as well. This angle will match that angle. This angle here at the center of the circle will match that angle at the center of the circle. Okay, the two, and again, you could reason all of that by CPCTC, because we already showed the triangles are congruent. Okay, so that's important to know, because I might give you a problem where I might say that this angle inside here is 71 degrees, and then I might ask you, okay, find for me the measure of angle BDC. Well, if you realize these two angles match, then angle BDC is just 71 plus another 71. It's twice as big. It's 142 degrees. Okay? You could even find something like this. I could ask you, okay, then what is the measure of angle BAD? B-A-D. B-A-D is just that one right up there. See that angle A at the top? Okay, well, notice you've got a right triangle. So if that's 90 and that's 71, we can just do some simple math here. I know a full triangle is 180. If I take away the 90 and if I take away the 71, the last remaining angle then has to be, and there's even a shortcut here. You know, instead of taking all this away from 180, you could just start with 90, because if this is 90, these other two add up to 90. So you could just take the 71 away from the 90. Either way, you're going to get the same result. You're going to get 19 degrees. So that last angle right there is 19 degrees, which again means this one's 19 degrees down there, because they're mirror images, they're reflections. Okay? Of course, the questions on these problems don't have to involve the angles. They might involve side lengths. You know, what if I told you on this same problem that, let's say that the radius here was 10, and let's say that this length along here was 24, and I said, all right, find DA. Okay, well, if you look, we've got, again, a right triangle there. See that? Going from there to there to there. Okay, and all right triangles, of course, have to abide by the Pythagorean theorem. A squared plus B squared equals C squared. I've got two of the sides. I'm trying to find the last side, DA. DA is across from the right angle, so it's the hypotenuse. Okay, I'm going to call it X for right now, but that's what we're trying to find is this side, dA, which is the hypotenuse. It's important you put that in the right spot, because if you put it in as one of the legs, you'll get a wrong answer. 10 and 24 are both the legs. And then, of course, you know what to do from here, I hope. Square each of these. Let's see, that's 576. Add those, you get 676. Do the square root at the end. And this one comes out to 26. So dA is 26. Okay, I could just as easily give you dA and have you find one of the legs, which means then that the unknown would move into here, and then instead of adding, you'd be subtracting. Okay, so it's just a matter of using the Pythagorean theorem, though, still. Okay? Now, I want to try a few more problems yet. Oh, one last thing, too, I want to show you. We talked about an inscribed polygon, meaning a polygon that's inside of a circle. Well, there's also polygons we can make that go around the outside of the circle. And the reason I bring it up in today's lesson is because that means that each side would have to be a tangent, like that. So if I draw a side that just touches the circle like that, maybe another one then down here, just touching the circle like that. Then I could draw another one maybe right here, just touches the circle like that. And maybe I just cap it off. Whoops. Let's try that again. Maybe I just cap that off like that, just touching the circle there. Okay, so each side of this polygon I just made is a tangent, just touching the circle at a single point. Okay, so then the polygon this time, instead of being inside the circle, is being wrapped around, you might say, the outside of the circle. So we don't call it an inscribed polygon. This polygon would be called a circumscribed polygon. To circumscribe means to go around the outside of something. Okay, so instead of inscribed inside, circumscribed means outside, goes around the outside. So a circumscribed polygon is made up of tangent after tangent after tangent for each of the sides. Now, keep in mind that you might have a problem on your homework that's something like this. They might say that this length from here to here, let's say, is 5 units long, and then maybe maybe they say something like okay, let's do this then. Let's say that from here, I'm going to move that. I just want to make this so I don't have to do too much erasing here. Okay, let's do this instead. What if I told you that, let's move that 5 to right here. Let's say that's 5, and then from here to here, let's say, is I did it again. Sorry. I'll get this right yet. Put that 5 back over here. And then let's say from there to there, from there to the point of tangency is 2 units long. Okay, and then they could ask you, like, what's the full length of that side right there? Okay, now, Don't forget my dunce cap effect that I talked about. If you pick a point on the outside, draw a tangent, the two tangents are both equal to each other. So if you look at this point right here, for example, that means from here to here is a tangent, from there to there is a tangent. If that's 5, this is 5. Okay, we're just doing that dunce cap effect. Same thing up here. See that point outside of the circle? From there to there is one of the tangents. From there to there is the other. So if this one's 2, this one's 2. So you can see then x in this case would just be 5 plus 2 or 7. Okay? So you might have problems like that where you might have to use the dunce cap effect, more than once. So this will match this, that'll match that. This will match that, and finally 1, 2, 3, 4. 1, 2, 3, 4. Those two will match as well. Okay, so you can technically find the whole perimeter of this whole thing if I give you just enough information. All right, now let's try some more problems here. I'll start you off with one of these with something as easy as this. Let's say that I've got a radius, okay, and then I've got this line and this line being drawn. And in these pictures, they'll specify that anything that appears to be a tangent is in fact so. So you see how this comes down and just hits at this single point down here? That's a tangent. See how this one comes up and hits right there? That's a tangent. Okay? So if I told you, for example, that that these were all right angles, okay, that would even emphasize that even more, because remember, a tangent meets a radius at a right angle. Okay, but suppose that's 19, and then I said, all right, find x. Okay, well, that's a radius, right, from the center of the circle out. This is a radius from the center of the circle out. These are all right angles, so that's got to be a right angle, because in a quadrilateral, all the angles add up to 360. You'll notice then that this is actually a square. 19 by 19, so this has to be 19 as well. Okay, so that's a nice easy one. Okay, another nice easy one would just be if I just did this. Tangent, tangent. This is 14, what's x? Okay, remember the dunce cap effect. These two have to match, so nice and easy on that one. X is 14. Okay, but they can get a little more difficult. What if I gave you tangent, center, radius? Draw that out to there. Let's say that this is 15, this is 20. Let's have you find this last side there. Okay, if this is the center of the circle, that's a radius. A radius always meets the point of tangent C at a right angle. Okay, thus creating a right triangle. See it? So we're going to use the Pythagorean theorem on this one. A squared plus B squared equals C squared. Okay, across from the right angle is my hypotenuse, so that should be my C, X. These two are legs, so they go in for A and B. 15 squared is 225, 20 squared is 400. My X is already by itself, so go ahead and add these. You get 625. Do the square root to get rid of the square. And this conveniently comes out to a nice whole number for you, 25. So there's X on that one. Okay, they can get a little bit trickier than that. Let's say there's the center of the circle. It comes down, it meets this tangent, sorry. That's a tangent down there. Okay, and let's say this is 21. They draw a segment out here hitting that. And this little segment here is 8. Just from there to there. And they want to know, I can erase the rest of that. They just want to know that. length, x. Okay, so again, we've already learned in this section that a radius meets a tangent at a right angle. Thus, this is going to create a right triangle. So again, we're using a squared plus b squared equals c squared, but be careful. The 8 is only this little part. We need this entire length along here to help us find x. Have you figured it out yet? 21, remember, is a radius going from the center. If I go from the center to there, that's another radius. So this should match this. This part's 21, just like that is. So the whole side along here of the right triangle is 21 plus 8, or 29. So that's the one across from the right angle. So 29 is going to go in for C. It's my hypotenuse. X and 21 are the legs. Again, it's important you get those put in the right spots in the Pythagorean theorem, or else you're going to get a wrong answer. 21 squared is 441. 29 squared, I want to say, is 484. Oh, I'm sorry. 841. I was way off on that one. Okay, now I want to get the x by itself, so I'm going to subtract that over to the other side. So I'm going to subtract a 441 off of 841. Notice that leaves you with 400. When you square root that, that conveniently, again, is going to come out to a nice whole number for you. That one comes out to 20 on that one. Okay? So be careful. Okay, that 8 on this problem was not the full length. You have to take the 21, the radius, swing it over here. 21 plus 8 then is 29. Okay, let's try one more. And then I think I'd feel confident you'll be well equipped to take on the homework. Okay, on this last one, let's say we've got a circle here. We've got a tangent line along the bottom here, just touching the circle at a single point. Let's say there's the center of the circle. We're going to draw then a couple of lines going out like that. And let's say that it's 30 from there to there. We're going to call this the x I want you to find. And then it's 40 from the point of tangency on out here. 40 from the point of tangency on out there as well. Find x. All right, now, I don't know if you notice it, but when I look at this problem, it almost is like begging me to go ahead and draw a radius to the point of tangency right there. And I know when I do that, when I draw that radius, it's going to come down and hit the tangent line at a right angle. So you see then it's going to make a right triangle out of it. So it is a problem, again, that's going to involve the Pythagorean theorem. Okay, now again, be careful though. This side over here I don't have, see? But it can be found. I mean, after all, I just mentioned that's a radius. When I drop that down from the center of the circle to the edge of the circle, that's a radius. And that 30 is also a radius, see it? From the center on out to the edge of the circle. So that 30 matches here as well. So that's a 30. Okay, and then I've got this side 30, that side 40. Basically, I need to find the entire length of this side, and then I can find x, see? So you could call this entire length x plus 30 and plug that in, but things get ugly then. I think it's a wiser decision to call this entire length a new label, not x, but maybe z. Okay? Just call it z for now, and then that's across from the right angle, so that would go in for the hypotenuse for my c. So I'm going to put a z in for c. And then 30 and 40 are both legs, so they go in for the a and the b. 30 squared would be 900. 40 squared is 1600. The z is already by itself, so go ahead and add these. You'll see that that adds up to 2,500. When you do the square root of that, you conveniently get a nice whole number again of 50. Now be careful, that's not the final answer. Remember, that's z up here, that was 50. So that means that x right here should be 30 plus what gives you 50? 20. So there's the answer. X is 20 on that one. Okay, so as you can see though, when you have a tangent meeting a radius, they meet at a right angle. So a lot of these problems involve the Pythagorean theorem. Okay, I think I've shown you enough to equip you for your homework. So for homework on this section on page 479 and 480, I'm having you do problems 6 through 16 and 31 through 36. Okay, and like I've been trying to emphasize, please put your name at the top and label the assignment so I know what assignment it was. Submit a completed picture of your assignment and be sure whenever possible to show work. Okay, we're getting near the end of this chapter. I've got one more section I'm going to cover, and then we're done with this chapter 9. We'll do review and then have the test, and then that'll be the end of the year. So I'll see you on our next section here.